So recording is in progress, and let's welcome you all and to take part in this upcoming first Gauge Gravity by the Ghat seminar. This online seminar series, it will focus on diverse topics in gauge and gravity theories. The seminars will be held roughly twice a month on the Wednesday afternoon and will bring together experts in the gauge and gravity theories. These talks will be recorded and uploaded on the CHEP YouTube channel and also other platforms. We hope this seminar series will bring together many of the experts who are working in the area of gauge and gravity theories and will become a platform for idea exchange and provide a fertile ground for seeding future academic activities. A set of instructions to be followed during the talk. Please mute yourself during the talk, except the speaker, of course. And the audience may ask the question in the end by raising the hands. And if there are any urgent questions, and then the audience can post them in the chat box, and they will be read later. So today we have with ourselves Yuya Tanizaki from Yukawa Institute, Kyoto University. He works largely in the area of non-perturbative QFT, symmetries, topology, resurgence, computational methods in QFT, QCD. And he has recently won award Siataro Nakamura Prize and Young Scientist Award. And today he will talk about some ideas on quantum tunneling from the Lefschetz-thimbles. So let's welcome Tanizaki-san and hear from him.
Yeah, thank you very much for this kind invitation, and thanks for giving me this great opportunity. So today, I'm going to talk about my old work about 10 years ago with Takayuki Koike, and I'm talking about some idea on quantum tunneling from using the idea of Lefschetz-thimbles. So let's begin with what quantum tunneling is. So classically, if we have a particle and assume that its particle has low energy, and let's inject this particle into this potential barrier like this, then classically what happens is this particle just bounces back with this potential barrier, and everything coming back to the original position. But quantum mechanically, something interesting happening. So counterpart of this particle should be a wave packet. And if we inject this wave packet to some finite height potential barrier, then what happens is when this wave packet collides this potential barrier, then part of it, maybe main part of it just bounces back. But there is a non-zero element goes through this potential barrier. And this is what quantum tunneling is. And it's genuinely quantum mechanical phenomena, as you can see that it doesn't occur in classical mechanics. And I'd like to, and the main purpose of this talk is whether we can understand this tunneling phenomena using path integral. So that is the main interest in this talk. And before talking about that application of Lefschetz-thimble technique to the path integral to understand tunneling, let me mention the close relation between tunneling and ground states. So let's consider quantum mechanics with this kind of double well potential and assume that this potential height between these two classical vacua are relatively high. So let's consider such kind of situation. Then classically, or if you consider a perturbation theory, then location of the vacuum or minimum of potential is just this plus A and minus A. And the wave function at the leading order perturbation or at any order of perturbation localizes on these two minima of classical potential. However, so this does not mean that in this quantum mechanical system, we have two ground states. So classically, it's true that there are two ground states or two lowest energy states, but quantum mechanically, so it does not mean that this quantum mechanical system have two ground states. Instead, actual ground state is composed by the superposition of these two classical vacua. So actual ground state should be equal sum of this psi plus and psi minus. And this fact is closely related to quantum tunneling. So, and let me remind why this is so. So in order to understand it, so standard trick is to consider this imaginary time developing operator. So usually, so in real time, we consider this kind of unitary time development operator. But let's take weak rotation and consider an imaginary time development operator. Then ground state of Hamiltonian is nothing but the maximal eigenstate of this e to the minus beta h operator. Then assume that this psi plus psi minus are good approximation of low energy spectrum. Then in order to compute energy eigenstate, basically it's good enough to compute this 2x2 matrix consists of psi plus and psi minus of the, so just consider a 2x2 matrix element of this e to the minus beta h operator using two good to approximate ground state and just diagonalize it. And in this way, we can obtain how ground state should behave. Then, because of the symmetry, parity symmetry, parity symmetry changing x to minus x, then if we consider this 2x2 matrix, then it is equal. Then first 1 component and 2 component are having an equal number. And let me normalize it to be 1. Then non-trivial thing is what is the off-diagonal component, which sandwiches e to the minus beta h with psi plus and psi minus. Then by considering some using the fact that this H is a real Hamiltonian, it turns out that this is a non-zero positive. There is a non-zero positive element in this off-diagonal component of this 2x2 matrix. Then that means that so in order to obtain the eigenstate, we have to diagonalize this 2x2 matrix. Then what happens is so eigenstate should form 1, 1, 1, 1, minus 1. And it turns out that so this first one, 1, 1, 1, 1 vector has a larger eigenstate of this e to the minus h, and which corresponds to the fact that the ground state wave function has to take an average of psi plus and psi minus. And this is what we are doing here. So let's consider this 2x2 matrix, and we try to compute its eigenstate. And this maximal eigenstate corresponds to 1 plus c, and this corresponds to a ground state wave function. And lower eigenvalue is given by 1 minus c, and it turns out that this is given by 1 minus 1. And in order to normalize it, we have to take the square root 1 over square root 2. And it turns out that so this should correspond to e to the minus beta ground state energy, and similarly this 1 minus c should correspond to first excited energy eigenvalue of first excited state. Then from this formula, we can compute this difference of the first and second first excited state and ground state energy eigenvalue. And it turns out that this delta E can be computed by, so since assuming that this difference is sufficiently small, then by doing the Taylor expansion of this summation of this difference, it turns out that this difference of the energy is given by basically proportional to this off-diagonal element of this 2x2 matrix. And in order to compute this off-diagonal element, you have to compute this imaginary time tunneling ratio. And it turns out that this can be easily computed, for example, by WKB approximation or a semiclassical approximation of imaginary time path integral. And it turns out that this is proportional to e to the minus instanton factor. So interestingly, so in the real time, so in real time phenomenon, so this operator is corresponding to this kind of oscillatory oscillatory integration. However, in order to compute this imaginary time of diagonal element, what you have to do is to compute this non-oscillatory functional integral. And moreover, important point is, so in real time, Lagrangian potential appears in the negative sign. But however, by doing this weak rotation to obtain this imaginary time propagator, what we obtain is this energy functional in the exponent of the path integral ways. So what we obtain is the kinetic energy plus potential energy. So compared with a real-time problem, so in imaginary time path integral, sign of the potential flips. Then also, so originally we start from this kind of WL potential, but in considering the imaginary time problem, what we obtain is, what we should consider is this kind of flipped potential. So you have to flip the sign of the potential. Then you can easily now, so now it is easy to find that there is a tunneling or instanton starting from one of the potential minima to another potential minima, because so originally you have to go through overcome the potential barrier, but now potential is flipped, so you can easily connect to maxima of the minus potential. And this classical solution is what we call instanton. And if we substitute that instanton solution into this imaginary time action, then what we obtain is this exponent. So this is the standard story to understand the tunneling phenomena in imaginary time formalism. So, and what we have learned in quantum mechanical textbook is we can, although it may be difficult to understand it in real time, but we can understand it in imaginary time formalism in semiclassical approximation. So everything looks nice so far. And what's the problem? So the problem is, so although it's true that in imaginary time path integral, we can understand instanton tunneling and interference of two classical vacua creates unique ground state. It can be easily understood, but still it's not. That does not necessarily directly mean that we can understand the real-time tunneling phenomena. And our motivation here is whether we can really, whether the folklore, so we would like to understand whether the conventional folklore, which says that the real-time tunneling phenomena is not a semiclassical phenomena, is actually true or not. And so we would like to understand whether, so what kind of formalism should be created to understand real-time path integral. That is our motivation to go one step further in this direction. And the usual logic for difficulty to understand the real-time tunneling phenomena in path integral is there is no classical solution that connects to classical minima of the potential. But here, more precisely, so what the problem is, so more precisely, this statement just states that there is no real classical solution that connects to local minima of the potential. And if we liberate ourselves from real valued function to complex valued function, so if we expand the region of the function from real valued function to complex valued function, then actually there is a classical solution connecting these two classical minima. And this is the key idea to go beyond this difficulty. So we would like to understand, so let me summarize. So far in imaginary time problem, we can easily understand the tunneling phenomena using instanton, and quantum tunneling becomes a semiclassical phenomena. But in real time, since potential barrier there is a potential barrier between these classical minima, we do not have a real semi-classical. There is no semi-classical way if we confine ourselves to the real valued function. And in order to treat complex valued function in path integral formalism, so idea of using complex valued function is not a new idea, which actually existed since late 70s or early 80s. However, so in order to treat such kind of complex valued function systematically, we had to wait until the development of Lefschetz-thimble path integral, which started around 2010 or 2013. And so let me briefly introduce what this idea of Lefschetz-thimble is. So Lefschetz-thimble path integral is a technique to treat oscillatory or technique to rewrite oscillatory integration into a sum of non-oscillatory integration, very roughly speaking. So precisely speaking, so oscillatory factor, there is a remnant oscillatory factor, but very roughly speaking, this technique rewrites a highly oscillatory integration into a sum of almost non-oscillatory integration. And around 2013, so this Lefschetz-thimble method starts to get attention in the context of the sign problem, because when we try to perform Monte Carlo simulation, if we encounter a situation where your path integral is quite oscillatory, then important sampling, idea of important sampling in Monte Carlo simulation does not work because of the cancellation between positive contribution and negative contribution, and that notoriously makes signal to noise ratio quite worse. And because of that, so people had for a long time, people have looking for a new technique that could circumvent the sign problem in Monte Carlo simulation. And around 2013, so people, for example, in Italy, like Cristoforetti, Francesco Di Renzo, or people in Tokyo, Fuji and Kikukawa and their collaborators have paid attention that maybe this idea of Lefschetz-thimble can be used to resolve the sign problem or make the sign problem much milder than the original path integral. And they are motivated from the famous work by Witten in 2010. And more precise formulation of this idea is if we consider this kind of path integral, which with oscillatory path integral factor, then using the originally, so this path integral is done for real valued function, which is here x of t. But now extending this real valued function to a complex valued function, then this originally oscillatory integration can be written as a sum of complex classical solution, and each this path integral where this new integration contour which span around, which goes through a complexified function, gives a new non-oscillatory integration, and original oscillatory integration can be rewritten as a sum of this kind of non-oscillatory integration labeled by complex classical solutions. And in order to make it precise, so let me consider this kind of finite dimensional integration where this weight factor here corresponds to is of x divided by h bar in real-time path integral. And originally, this integration contour m is taken to be, for example, taken to be a real region. But in order to apply the idea of Lefschetz-thimble, we complexify this m to so originally, for example, this m is roughly just a real line, But now, starting from a real line, we now consider a complex plane instead of just a real line. And now we look for a well-defined integration of this complexified function. And in order to do it, originally, for example, even if you start from a simple function like ix squared, then in this real line, this is just oscillatory, and you can make this integration convergent. But if you consider a complexified region, then it turns out that for this region, e to the ix squared goes to 0 in this blue region. However, in this yellow region, e to the ix squared goes to plus infinity, and integration does not converge if we just sum up all possible complex functions. And the idea is originally integration contour just goes this purple line. And by using the idea of Lefschetz-thimble, so idea of Lefschetz-thimble is to deform this purple line, just rotate it like this and connect this well-convergent region. Then along this green line, so original oscillation given by e to the ix squared is just now Gaussian damping factor, and there is no remnant oscillatory factor by doing the continuous deformation of the real contour to a complex contour. And for this purpose, we have to find a convergent region in this complexified space. And this is basically characterized by where this exponent, characterized by the region where this exponent is sufficiently negative. And Lefschetz-thimble, could you mute? Sorry, thank you. And the convergent region is given by this region where exponent is sufficiently negative. And the Lefschetz-thimble can be constructed by what is called this gradient flow equation, where we have to take complex conjugate. So in the standard gradient flow, this complex conjugation does not exist, but in order to construct a Lefschetz-thimble, we have to take a complex conjugate on the right-hand side of the gradient. And if you make a correction of the flow starting from the saddle point, so starting from this saddle point and solving the gradient flow that emits from this saddle point, then you can construct a Lefschetz-thimble, which is now just this green straight line with 45 degrees. And it turns out that this Lefschetz-thimble forms the basis of this relative homology, which is relative homology. And basically, this Lefschetz, so if you construct this Lefschetz-thimble, you can find all possible convergent integration contour when you take sufficiently large T. And by constructing Lefschetz-thimble like this way, then it turns out that original integration, this Z, which is
Yuya, there is a question.
Okay, let me check.
Somebody is asking, Chetan is asking, what is T in the definition of CT?
Okay, this T can be an arbitrary number if it is sufficiently large. So you can show that as long as T is sufficiently large, this relative homology does not depend on T. So this T is just an extra parameter in order to judge whether this integrand is becomes sufficiently small and the integration contour can be given or integration along that contour should be convergent or not. Okay, so using this kind of Lefschetz-thimble, or it is a multi-dimensional version of a steepest descent contour, and using that kind of quantity, then any integration with this integrand can be expanded in this way. And another important property is, so if we pick up one Lefschetz-thimble or one steepest descent contour, then integration along that Lefschetz-thimble has a well-behaved, have a nice behavior in the semiclassical limit as we take h bar goes to 0. So basically, so important exponential 1 over h bar dependence is completely characterized by the action of the classical action at the complex classical saddle point. And if you take a Gaussian integration or doing a perturbation along that saddle point, you can construct a well-defined perturbative series expansion of this original integration, of this full integration along Lefschetz-thimble. So in other words, so this kind of decomposition makes original full integration into makes a well-defined decomposition into an asymptotic expansion for the partition function. And since we know that, so this originally, so semiclassical, so tunneling was a semiclassical phenomenon in imaginary time formalism. So let's try to apply this technique to a real-time path integral, and we would like to understand whether quantum tunneling can be actually understood like this way or not. And before going to tunneling phenomena, so in our paper, we tried whether we can reproduce the correct behavior of the harmonic oscillator using the idea of the Lefschetz-thimble. And it actually works. So if we consider just a usual harmonic oscillator, then so if we take if we just compute this kind of Feynman propagator, Feynman path integration kernel. So we computed this quantity, and it turns out that, so if we just compute this kind of path integral, is x over h. So this is the original integration what we wanted to do. X0 is xr and xt is xf. And we rewrite this integration.
I have a question.
Mm-hmm.
The Maslow index that comes up in this example that you discussed.
Yes.
Is it because is there a connection to the relative homology that you talked about 2 slides ago?
Yeah, it actually is. So let me explain, including it. Yeah. So what we wanted to compute is this integration, and we wanted to perform the Lefschetz-thimble path integral. So originally we computed this one, but now, so we would like to compute this now complexified integration, and now integration region becomes a Lefschetz-thimble. And we obtain this factor. And since this is a just a quadratic system, so it turns out that so along this Lefschetz-thimble, this is just negative definite, and this integrand is just a positive convergent function. But it turns out that so this measure factor is basically what we are doing is originally, for example, if we just consider this kind of integration, then originally integration contour was this, but we have to look for a steepest descent contour, and we needed to rotate it into plus pi over 4 degrees. But if, for example, if we consider another integration like minus ix squared, then original integration contour was real, but now rotation should be minus pi over 4 instead of plus pi over 4. And this difference, plus pi over 4 and minus pi over 4, turns out to, so this tension of of rotation direction of depending on this sign, basically gives a y mass loss index appears in this Lefschetz-thimble path integral. So it turns out that so how this Lefschetz-thimble intersects with the original real-time contour turns out to give a correct Maslov index factor in this harmonic oscillator Feynman kernel. Anyway, so what we have checked using this simple example is so at least in this solvable example, idea of Lefschetz-thimble works perfectly, and it reproduces the correct factor, correct formula, including this non-trivial Maslov index, topological index contribution. So this is what we have observed, and we are convinced that Lefschetz-thimble method could be used to consider a real-time path integral into a nice convergent form. Okay, so now let's go into a more complicated example and whether we can understand and let's discuss whether we can understand the quantum tunneling phenomena using real-time path integral. And for this purpose, what we have considered in our paper is we consider a double well system like this.
Yuya, there is a question.
Okay.
Somebody in the chat box has asked if we take that angle as a variable, are there something like stable, unstable angle values?
Okay. So in this case, so this direction is convergent and this direction turns out to be divergent. So you may say that this green direction is a stable direction and this purple direction is unstable direction, something. And in this case, this is something. Is there any equation of motion for the angle? No. So this angle is completely specified by solving this gradient flow equation. So it is just defined by solving this gradient flow, and basically this gradient flow fixes which direction is stable and which directions are unstable. I assume it's so now. Okay, so now let's move our interest to a real quantum tunneling phenomena, and so for that purpose, let's consider a double wave system. So now potential is really just like this. And here I said classical minima is located at +1 and -1 in x direction. And we would like to understand whether real-time path integral starting from -1 to +1 is can be well described by this complex classical solution. So this is what we would like to understand. So, or in other words, what we are computing is x equal +1 e to the -i 8. So IHT x equal -1, and rewriting this as a path integral with x naught is -1, x t is +1 e to the is x over h1, and we are trying to apply Lefschetz-thimble technique to this path integral expression. So this is what we are doing now. And as a first step to apply a Lefschetz-thimble, we have to look for a classical solution, a complex classical solution. And constructing a Lefschetz-thimble is actually a tough work, but basically without finding a complex classical solution, we can do nothing. So what we are doing first is to find a complex classical solution of this system. And we can actually easily find a complex classical solution of this system using the energy conservation law. And it turns out that so since in this WL system, so we can describe the classical solution using Jacobi elliptic functions. So solution of this energy conservation can be actually written like this way. And in order to label, and it's relatively easy to find that this energy conservation is satisfied with this form, but we actually need to find how this complex solution is labeled with this boundary condition. And in order to see how many solutions exist with this boundary condition, we have to notice that so elliptic functions have a double periodicity. And it turns out that because of this double periodicity, so there are two labels, two integer label for a classical solution, complex classical solution. Satisfying this boundary condition. G of 0 is -1 and G of t is +1. And we actually find that so this how this label can be related to this label P, complex energy P, by using this kind of formula. And we actually find that there are so infinitely many classical solutions satisfying the boundary condition. So now we find a candidate of this complex classical solution in the Lefschetz-thimble decomposition of this real-time path integral. But this does not immediately tell which complex solution is actually responsible for quantum tunneling phenomena. And so as a next step, what we have done is to give a educated guess to understand what kind of classical solution is giving a dominant contribution to the real-time tunneling phenomena. And first, our original guess is if we start from imaginary time instanton solution and going back to the real-time tunneling and considering the inverse Wick rotation, so our naive guess is by considering this procedure, we may be able to obtain a real-time tunneling phenomena. But this actually didn't work, unfortunately. So if we consider imaginary time instanton and performing the inverse Wick rotation with given same label parameter n and m, it turns out that this just gives us Farellon-like contribution, or it turns out so originally in imaginary time, so what happens is originally, so this instanton solution have almost zero momentum and it stays for a long time in the classical saddle point. And then there is a tunneling and it stays another classical solution. So this is really looks like tunneling. But if we just perform an inverse Wick rotation, what we find is, although it starts from classical minima, this has a large real momentum and just goes over the, just sits on the top of the well between these classical minima and stays for long, and now again rolling back to a classical solution and reaches another classical vacuum. So this, it turns out that if we just naively inverse Wick rotate, we perform an inverse Wick rotation of imaginary time instanton solution, so that kind of a solution have a large energy that can go over the potential barrier and connect to classical minima in a classical way. So unfortunately, so our naive guess didn't work, and we did a more hard computation to find out what kind of solution, classical solution, looks really like a tunneling. And what we find is if this N and M labeling this complex classical solution have sufficiently large, which is comparable with a tunneling time, then that means that so there are very many number of complex oscillation occurs in this kind of classical solution. But if we take a make a plot with this kind of label, then it turns out that so solution stays on a classical minima for a long time, but it starts to largely oscillate and in a complex direction, and now stays on another classical vacuum. So instead of going through a real path, but by going through the potential height, top of the potential height in an imaginary direction, then it can connect to classical minima with a reasonable in an instantaneous way. So this is really more looks like an actual tunneling phenomenon. And this is fit our original expectation of the tunneling phenomena. And this picture is not only given by our work, but also by Alexei Chama and Mithaus Unda around the same time. And actually, so if we just plot like this, it's a bit difficult to understand what is actually happening. So let's plot this actual tunneling-like phenomena in a complex plane. Then what is happening is originally in infinitely negative path, it stays on one of the classical vacuum. Then it starts to it starts a small complex rotation around this classical minima for a long time. Now and near the tunneling region, so it starts to, so this oscillation grows like very large, then goes through this top of the potential height in an imaginary direction. Then now it starts to oscillate like this, and now it converges to a classical minima, another classical minima. So, and in this way, it turns out that so action or exponent of this path integral of this one for this classical solution turns out to be negative order 1 number. And furthermore, Alexei Chama.
Yuya, we have a question. What is the significance of the red curve in the last slide?
Oh, okay. So sorry, I didn't explain. So this blue part is a real part, and this red part is an imaginary part. So sorry, I forgot to mention. Yeah. And this is very important because if we just having a real part, then with this kind of large oscillation, then action has a large real part. But because of this, because this oscillation happens simultaneously into a real and imaginary direction, then oscillation, so contribution to the action turns out to cancel out. And so this I times S turns out to have a turns out to have a very small imaginary part, and I to the S just turns out to be just order 1 negative order 1 factor. Yeah. So this the fact that this oscillation happens simultaneously into real and imaginary direction are very crucial to show that this exponential path integral weight have an instanton-like damping factor. And actually, so the work by Alexei and Mithaus shows that in the infinite time interval limit, this actually converges to the instanton factor exactly. Yeah. And this is giving another convincing evidence that this kind of solution is responsible for the tunneling phenomena in real-time formalism. But okay, another question. Does the red curve in the G plane has some relation with the spiral? Oh, I do not know what that spiral is, so maybe we can discuss later after that. Yeah, if you can tell what it is. Yeah. Okay. And yeah, it's almost now finished. So this is the so far I talked about our analytic work, but what is very surprising or fascinating development given done in recent year is now people in KEK, Jun Nishimura and their student Sakai and Rakov studied this real-time system, real-time quantum phenomena using numerical Lefschetz-thimble method. So people have developed a numerical technique to apply the idea of Lefschetz-thimble to overcome the sign problem in many, for example, in many body quantum mechanics. But it turns out that that technique is powerful enough to apply to understand the real-time path integral directly using the idea of Lefschetz-thimble. So also what they are doing is not Lefschetz-thimble itself, but using the idea of generalized Lefschetz-thymble. So they have succeeded to understand the real-time tunneling phenomena using real-time path integral. And furthermore, what is interesting is, so what they are doing is basically a Monte Carlo simulation. Yeah, very roughly speaking, on Lefschetz symbols. And they show that they picked up some important configuration in this Monte Carlo simulation, and they show the figure of their solution like this. And what they find is, so if we pick up some random configuration appearing in this Monte Carlo, then that complex contour looks like this, or looks like this. And which is quite similar to, although this small spiral region have not seen, but they observe that this kind of part of the spiral behavior is actually observed in numerical simulation. And I think this is quite fascinating. And another important comment is, so what our work did is a computation of the Feynman kernel. So x equal +1 e to the minus ith x equal -1. So what we have computed is this Feynman kernel, but their work is doing this kind of minus ith psi plus, and important difference appears in the wave function, and these wave functions are roughly a Gaussian wave packet. Located around each classical vacuum. And compared with this delta function-like boundary condition, so this Gaussian wave packet only have a low momentum contribution. And because of that, so this kind of Feynman kernel has a contribution from this kind of spiraron-like or large momentum contribution. And this spoils the leading, and because of that kind of messy contribution coming out of this high energy contribution, so tunneling phenomena is basically obscured in this kind of Feynman kernel. However, in their work, instead of studying a delta function like Dirichlet boundary condition, they use the Gaussian wave packet, and that restricts, and because of that, so real momentum coming out of this wave packet is almost or is sufficiently small, and because of that smearing, they are succeeding they succeeded to extract a real-time phenomena quite nicely. So I'm expecting that although their work is basically based on numerical method, but I think combining this idea, so we may be able to describe real-time real-time tunneling phenomena in an analytical way using this kind of smeared wave function. That is my hope for the future development of this work. Okay, so let me summarize. Let me summarize my talk. Although real-time tunneling phenomenon is usually quite tough in real-time path integral, but the Lefschetz-thimble method may give a new tool to understand it. And the idea is Lefschetz-thimble method give a systematic way to treat a complex classical trajectory to control the oscillatory integration. And because of the development of the idea of Lefschetz-thimble, so we can now systematically treat the complex classical trajectory, and they may be a significant. They may play a significant role to understand the quantum tunneling phenomena in real-time path integral. And as I said, in this study, we use a Dirichlet boundary condition as initial and final state, but recent development or recent observation done by KEK group suggests that if we use this Gaussian wave packet instead of Dirichlet boundary condition, so now semiclassical description of real-time tunneling phenomena, it becomes much better, and we may be actually able to describe real-time tunneling phenomena in an analytical way in near future. Although I'm not, this is optimistic, but this is my hope. Yeah, so thank you very much for your attention, and let's take questions. Yeah.
So Yuya, we have two questions. So
yeah,
chat box, and
okay.
one
First
is
one
from
is
Sumati.
why the spiral behavior does not appear in Monte Carlo simulation. So I see. Yeah, so I'm not totally sure about it, but my expectation is now what they are doing is this Gaussian wave packet. So wave function is smeared around this region. So I think so because of that smearing, this small spiral cannot be yeah, my expectation is because of this Gaussian smearing, small spiral region is already smeared, and they can only observe large spiral region. So that is my expectation. Yeah. And the second one is nice to understand how Markov-Chain Monte Carlo can be used here. What replaces the transition probability from one step to the next in the Markov. So yeah, so there are several techniques that can be applied to Markov chain Monte Carlo, and so there are various techniques like so actually so I cannot list up all possible technology, but for example, people are developing the numerical technique to study this kind of sign problem, path integral with sign problem into non-oscillatory integration using what is called generalized Lefschetz-thimble. And there are several techniques like hybrid Monte Carlo, combination of hybrid Monte Carlo, etc., to systematically update the configuration along Lefschetz-thimble or along generalized Lefschetz-thimbles. Yeah. And another one is finally by using Lefschetz path integral, the sign can be resolved. So strictly speaking, so we cannot completely resolve the sign problem, even using this kind of Lefschetz-thimble or generalized Lefschetz-thimble. And the difficulty is so there are several contributions. So first one is, so this part is completely positive, definite, and convergent, but there is a major factor. So there is a sign from measure from Jacobian. And another one is we are summing up different complex classical solutions. And on each classical solution, this exponential factor has a definite sign, a definite phase factor. But among different complex classical solutions, there can be interference between them. And so there are several remnants of the sign problem. And another question is, if I understood rightly, to evaluate something integral using correlation, one has to deform infinite real integration contour to infinite Lefschetz-thimble. Now finding these Lefschetz involves solving flow equation. Yeah, that's true. The question is, are these flow equations are coupled or not? So they turned out to be a coupled equation. So actually, actually, obtaining the Lefschetz-thimble is usually a tough work, and because of that, so numerical Monte Carlo is important technology to understand what is happening, and in this context, yeah, their work. So the work by KK group give a fascinating finding. Actually, that actually, so our work is our work 10 years ago was just a speculation, but their work give a strong evidence that at least roughly our picture of the quantum tunneling seems to be correct. Yeah.
Yuya, I was just have a small question. So in one of the slides, you mentioned about something called a small n sigma.
Small n sigma, yeah.
So that is, if I understand, some kind of a number. So like, is there a systematic way? Yeah, this slide. Is there a systematic way of fixing n sigma?
Yeah, so there is a mathematical formula determining n sigma, but actually, so actual computation is quite tough, and it's quite difficult to compute it in complicated or coupled system. But in numerical general Lefschetz-thimble method, basically, what people are doing is to deform n to a summation of n sigma, j sigma directly, without directly obtaining n sigma and j sigma independently. So at least in numerical Monte Carlo application of numerical Monte Carlo, this is automatically done without without concerning what n sigma is. But in order to understand the analytic result, so we have to understand n sigma, and that is a bit complicated part. Yeah.
Okay, thanks. Can you share the reference on this how to compute this n sigma, in a systematic
Yeah.
way?
Okay. Right. Yeah. So
maybe you can put it in the chat box
later by email or something.
or send it in the send it to me, and we'll.
Okay. Yeah. I'll do.
Yeah.
So I have one question. I have two questions which are sort of related to each other. How do you see this generalizing to path integrals in more than one dimension? And so the related question is, how do you see this being applied to study quantum gauge theories?
Yeah. Let's see. So extension to higher dimension is, let's see. Yeah, so at least, so if we decide that we perform numerical simulation like them, so having multi-dimension does not necessarily give a severe difficulty. So although, of course, numerical cost becomes large, but I think that's still doable. But on the other hand, on analytic side, so in order to find this kind of classical solution, so we use the fact that so this kind of classical equation motion is reduced to a well-known differential equation, and in this case, so somewhat luckily we can find that all classical solution obeying this equation can be, so we using the fact that this differential equation has a solution of Jacobi elliptic function, we could systematically obtain all classical solutions. So on that side, so if we have a multi-dimension, this becomes much this becomes much difficult on analytics. But if we decide to perform numerical computation, I don't think this is very difficult. Yeah.
And how do you see this being applied to study gauge theories?
Yeah, on gauge theory, let's see. So if we, what kind of, I'm not sure what kind of problem is related to this tunneling phenomenon. So let's see. So actually, my original motivation is whether we can understand, for example, nuclear fission phenomena using real-time path integral or not. Of course, that is quite, I know it's a quite tough work, but I was wondering whether there is a new systematic, so if this kind of technology can give a new systematic technique to understand fission or fusion phenomena, because there, so tunneling phenomena plays a seminal role in order to understand them. So maybe if we consider some other good system, like for example, in field theory, so also in field theory, if we consider this kind of potential, and if we start from this kind of metastable vacuum, and then we believe that if we at least if we wait sufficiently long time, there is a vacuum decay to from this false vacuum to actual vacuum. So if we of course, so applying this kind of technique to field theory is still a big dream, but if we could proceed and eventually develop such kind of systematic technique based on this idea, maybe there is a nice application to also to field theories. But that's still a long path to reach it. Yeah.
Okay, thank you for the answer.
So are there any more questions from the audience? If anybody wants to ask something more.
So I have a question. Can I ask?
Yeah.
Yeah. So I just want to know that what is the spiral curve? What is it signifying physically? Like, to me, it appears that when we do the spirals, like the angles are continuously changing and the amplitudes are decaying. So is it like that, or is it somewhat more going on?
Yeah. So what is happening is let's see. So elliptic function has a double periodicity. So basically, so at least in this kind of small region, so there is roughly two direction of the oscillation, and n and m, that is user level here, is basically a number of oscillation along each direction. And so by taking large n and m, it basically says that there is a simultaneous oscillation on each direction, and by summing up, and as a result, it gives this kind of spiral kind of behavior appears by taking this large n and m, because it should have a very large number of oscillation on each direction.
Okay, so are these the oscillations like basically decaying the amplitude, like as you were showing in the blue and red curve? Red stands for the oscillations and blue stands for the decaying.
Yeah, let's see. So decay. So tunneling rate, or so if you mean the decay rate or tunneling rate, then that should be determined by the action instead of this. Yeah. So I think so. Important contribution to this to this negative factor is basically coming out of this large region of the spiral, because small region of the spiral that just almost rotates in the vicinity of the classical action. So that part doesn't contribute much to the decay factor. So or yeah, or instanton factor. So main contribution to the instanton factor coming from this kind of large region spiral. Yeah.
Okay.
So anybody else? Any other question?
Yeah, I have a question.
Yeah.
You have this on the next slide, I think, or the previous one, n over t, m over t of order 1.
Oh, this one? Yeah, yeah.
But t is chosen arbitrarily, right? It can be anything, right?
Yeah, right.
So then which solution, which Jacobi function contributes is also different in different cases?
So in this case, so if we take n and m is both order 1, and if n and important number is n minus m or m minus n, and so if we have k here, then what is happening is basically so starting from here and going like this, and this is the situation when k is 1. But when k is sorry, screen share. Oh, yeah. Yeah, so if n minus m is 1, then this is the situation when n and m is 1. But for example, so when n minus m is 2, then what is happening is, starting from here, going like this. And furthermore, it start again rotate like this and coming back. So basically, this difference of n and m basically counts the number of tunneling within this time interval. Yeah. So as long as when t is sufficiently large, and then when n minus m is 1, it's just like this. But when n minus m is 2, it goes something like this, etc. So important contribution is basically coming from the contribution when n and n minus m is just 1 or something.
Okay.
Yeah,
so then this t parameter is not really important then in that case.
Yeah, t parameter is not so important. Yeah, although n and m must be comparable to t, but yeah, important factor is the difference between n and m.
Got it. Thank you.
So Yuya, I want to ask one thing. So these so characterizing this classical solution using n and m, suppose that we plug this solution back into the action of the theory. So you get basically the classical action, and they will depend on n and m. Now, suppose the action also has a topological term, and those basically, which is a total derivative. So they will not affect your equation of motion. But when you these kind of solutions which are depending on n and m, when you put them back into these topological terms, they may have different values for different n and m. So is there any such thing that you observed, like there are different topological sectors corresponding to different n and m?
Let's see. But in this case, it's just a simple WL system, so there is no counterpart of the topological. Yeah. So of course, it's an interesting question whether we consider a more non-trivial system like a particle on S1 with cosine WL cosine potential. Then we can consider a theta term, and contribution to the theta term is yeah, should be quite interesting, but we haven't checked it. So yeah.
I see. Okay. Okay. Thank you.
Yeah, there's a message in the chat, I think. For in Sigma, there are papers by Witten, is it? Was that the reference you had in mind?
Yes, right.
Yeah, Chetan has mentioned some papers by Witten, which is also discussing about systematic computation of n sigma. Okay, any more questions from the audience? We do not see any more question and nothing in the chat box also. So shall we conclude this session?
Yeah, thank you very much for your attention. And
thank you, Yuya, for the very nice talk and giving us a very wonderful presentation on the tunneling. And we apologize for the last minute arrangement of the rescheduling of the talk. We are sorry.
No, that's not.
But we are very glad that you accepted and also agreed to reschedule it. So thank you very much. Thank you.